Yeah, so my name's Chase Douglas. Am I coming in all right? It's actually surprisingly hard to tell back here. So, yeah, as was mentioned, I'm the co-founder and CTO of Stackery. We're software that accelerates teams building serverless applications. And as we've done that over the past few years, it's been really interesting to work with a bunch of companies that have different needs, different challenges, things where they recognize the power of serverless technologies and what it can do for them, but they still have to deal with legacy systems maybe. Things that were not built in a serverless, horizontally scalable fashion. And they've had to figure out the right ways to integrate some of their existing technologies using the new approaches of serverless. And today I kind of wanted to talk through some of these design patterns that have addressed some of the more challenging architectures. And again, this is based on specific applications that either we have helped build or helped our customers build. Hopefully it's very thought-provoking, and as mentioned, there will be time for Q&A at the end to get into any nitty-gritty details. But to start out, a little bit about myself. I tend to seek out very challenging technical problems. I'm the CTO at Stackery, figuring out how all the architecture of serverless works and how companies need to build serverless. But before that, I've started in the Linux kernel operating system level. That got me really interested in playing around with things like multi-touch input systems. I had this Apple Magic Mouse that I got around the same time that I started working at Canonical, the company behind Ubuntu Linux. And I was just so fascinated with the technology. It evolved into me building device drivers into the Windows system, really enabling multi-touch into for the Linux desktop. I left there. I wanted to kind of move into higher orders of software development, into web applications. And I was a technical architect of the New Relic browser performance monitoring solution, where we were injecting multiple kilobytes of minified JavaScript code into page loads across the internet. We were really the first product that kind of provided instrumentation around error handling and AJAX timing, session traces for browser-based applications. And now it's all about serverless. It's this new realm, as Chad was talking about earlier today. It's where everything is going to be in the future. It's still early days, but there's a very promising technology platform. We need to come up with the architectures and the tools around that. So that's what I focus on every day. So we're going to talk about serverless solutions for non-serverless problems. And in particular, there's three that I've found are rather interesting from things that we've helped customers in the past with. Working with SQL databases, tends to be non-horizontally scalable. So how do you do that effectively? How do you do rate limiting? We're going to talk about an example where maybe you want to scrape some website pages, but you want to be a good netizen and not do that at a ridiculous scale. And finally, how can you build state machines with this new technology? There's a lot of building blocks there, but if you really want to build arbitrary states, how do you hook it all together? So we'll start talking with how you can integrate SQL databases with a serverless solution. You may have your own pointy-haired boss who comes to you one Monday morning, and he says, "We've been tasked. Our CTO says that we need to build a new API to access data that's already existing in our production MySQL database. We don't have a choice here to go and refactor things, to build it on a DynamoDB table or some other horizontally scalable NoSQL service. But maybe because you've got some experience with serverless or coming from the conference this week, you've got more excitement around the possibilities. You think to yourself, how hard can this be? I can certainly build a serverless solution, AWS Lambda for my compute, API gateway for the REST API. This should be trivial. All I really should have to do is create some functions where I add my favorite ORM and database driver, and I connect to my database, I query, and finally we profit, just like we do with any other solution, container-based, VM-based, pure server-based, in case anyone is still doing that. In fact, this is common enough of a requirement that early on, and it's still on AWS's website today, they had this example where they are showing some Python code. Very simple. You've got an AWS Lambda function. When it initializes the first time at what people refer to as like a cold start, so you're not running, when a function runs the first time, it boots and it runs through all of the code to initialize, and then it runs the handler function. On subsequent invocations, if it hasn't, the cached function instance hasn't expired, it'll rerun just the function handler code. So what they suggest here is, well, instead of creating a connection on every invocation of your function, you should create a connection when your function is first initialized at that cold start time. And it's a really cool technology that they've implemented here. The possibility that you can have these cached function runtimes, and they can be frozen for minutes, 10, 15 minutes, maybe even up to an hour. And they can be paused and then resumed when the next message for an invocation comes in. And the underlying Lambda system will keep your network connections open in the interim. It's actually a complex system that's TCP IP-based networking systems. You oftentimes are sending little like ping messages back and forth just to ensure, is this connection still live? I think it's impressive that they built into the system the ability to keep these network connections live in between invocations. So they love to show that off and say, okay, you can do this. You can create one connection at the beginning of your initialization. It's going to stay warm for you when your functions are reinvoked. But just like in the olden days when people would create these maps, we didn't know what the whole world looked like. It was all brand new. We thought we knew. We had these really interesting diagrams, but there's, at least in the old days, the maps would say something like on the edge, like, here be dragons. We don't know what's over there. You might just like fall off the earth even. Unfortunately, in this case, some of the documentation and examples don't really even touch on that. But trust me, there's a lot of dragons, here and there when you're mixing serverless and non-serverless technologies. So you took their AWS's example, you built it, you pushed it out to production. All of a sudden, your users start to tell you that they're seeing errors, or maybe your error monitoring service is telling you this. You see that you're hitting this issue where there's too many connections to the database. And you think to yourself, I'm not really sure how that could be. I'm looking at some graphs and some charts. My throughput hasn't changed much in my system. But at the same time, I am seeing these errors spiking. So, what's happening? What's going on here? And to answer this question, as with most things in engineering, we need to kind of step back and think through the logic of some of our base assumptions. And if we think about it, as I mentioned earlier, most SQL databases, relational databases, they're not serverless friendly. Now, when we speak of something being serverless friendly or not serverless friendly, usually what this boils down to is this horizontally scalable? Can I trivially just add more and more capability to the system? If you've got a NoSQL database like DynamoDB or Cassandra, even if you're managing it yourself, the way that those systems work and store their data is based on key values types of storage solutions where to create more capacity, you simply add more nodes to a cluster, you reshard the keys, and things just evenly distribute. But when it comes to relational databases, if you want to scale that up, there's a certain amount you can do by just increasing the instance size. But at a certain point, you have to create an ability to have more instances, potentially because of either how you need more data in your system, though a lot of times that can be solved using networked file systems. It could be because you need more connections, network connections. And that's really starting to get at one of the core challenges of marrying serverless technologies and databases is this network connection limitation. It turns out that most SQL databases have intrinsically network connection limits. So why is that? Well, each database connection traditionally in these database systems that were created in the 80s, the 90s, the 2000s, they handle connections on independent threads of execution. So at an operating system level, what this means is that you have a lot of sequential, programming steps that you go through. This is what we as humans develop. We write our code, and we tend to think in terms of one thing is going to happen, the next thing is going to happen, the next thing is going to happen. But as we all probably understand, there's also mechanisms for parallelism. So the way that we generally do this, at least the way that we did it in the past, is by using threads of execution, which is instead of having separate processes, which are extremely heavyweight, we have these lightweight POSIX threads. They still have, because you've got like a bunch of, maybe 40 of these threads going on in the same process. It means you still have a bunch of different stack traces of execution, one for each thread. You have different storage locations for the thread called thread local storage. And so this was a key technology that was developed that enabled multi-processing or multi-threaded, multi-core processing within a process. But it has some downsides, and that's that every thread requires memory resources to be set aside for it. If you're spinning up a database, you have to set aside up front, say, like, I'm going to have 200 connections to my database. So I'm going to set up 200 threads. Because if you try and set up threads dynamically, that as well takes a bunch of resources. So you're going to set up a pool of these threads in the beginning. So we've got this system that has this hard limit on a number of connections. But that starts to become problematic with a serverless, horizontally scalable solution. So our fundamental problem, if we go back to the example that we got from AWS, our fundamental problem is that we've got a bunch of these function instances where we're connecting to the database, but then those functions go idle. They sit around for 10, 15 minutes at least, just waiting for the next invocation request. And while they're doing that, this network connection is still alive. It's never closed. It's never terminated. So we're holding on to these network connections and we're preventing other functions from being able to use it. And you might say to yourself, well, yeah, but this shouldn't be a problem because the next message that comes in that would need to use a network connection to the database is going to invoke this same function. So it's okay that it's keeping that database connection around. You have to kind of dig in a little bit deeper to figure out where does this become actually problematic. Well, let's look at an example. Here we've got an API. It's got 5 endpoints, each that are implemented using an independent function. So each function, as they run, they have their own connections to the database. And when they become idle, they keep their own connections to the database. So let's say that we've got an amazingly homogeneous API where there's 20 concurrent API calls for each endpoint at the same time. Now, if our database maxes out at 120 connections by default, that's okay. We're using 100 connections here. So this isn't a problem. But this is hardly ever how real-world APIs function. Real-world APIs have traffic that shifts around between endpoints. So now, let's say that a minute later, we've got 40 concurrent connections to the list users function. And we've got only 15 connections among the other 4 functions. So we still have 100 total requests being made at the same time, just as before. But now what's happening is we've had to spawn 20 more instances of the list users function. Meanwhile, we've got 5 idle instances of the other API functions. So now we're hitting 120 open connections between both idle functions and running functions. That's the maximum that our database can handle. So if we go a little bit farther and we shift traffic one more time, now we're over our database connections limit. And everything falls apart. So we got a couple of things we could do about this. Solution one, and I first developed this talk back shortly after AWS at reInvent last year had announced this pretty cool sounding technology called Aurora Serverless. Aurora is their highly scalable database clustering solution for relational databases. And they introduced this new service that wasn't available yet, but they said it's coming soon, and it's called Aurora Serverless. It's really cool because it's basically auto-scaling MySQL-compatible databases. That's awesome. That's perfect for so many of my use cases. And I thought it was cool enough. It's not like it had no limits. They specifically talked about how it doesn't. You can create all kinds of networking connections to this, and it doesn't. There are no limitations on that. When it actually released, I found out, well, that's halfway true, but there's still some tricky bits to this. We still need to manage our connections because, as it turns out, the way that it auto-scales is half based on the CPU utilization of your cluster, but half based on how many network connections you're using. So if you're still spinning up tons of network connections, then yes, you have the capability to do that and not worry about the system falling over, but you're going to be over-provisioning your system and paying through the nose. So we still need some other solution for this issue. It's actually quite simple in hindsight. All we really need to do is say, yeah, it's great AWS that you can keep those network connections live, but instead, I'm going to go and create a connection to the database every time my function invokes. And there's a reason AWS likes to tout that they can keep these connections alive, cached, while your function runtime is cached. So you might ask yourself, or ask me, I should say, wait, doesn't this add overhead on every function invocation? Isn't that something I should be concerned about? And the answer is, yeah, it does. It's true. But at the same time, think about what is the use case for your API. If you measure this overhead, then there should be some threshold at which you say to yourself, the overhead is reasonable or it's unreasonable. And more often than not, the overhead is oftentimes very reasonable for your use case. For example, we spin up lots of databases for our own developer environments at Stackery. Every developer gets their own environments, and all of our functions that run for our APIs, for our backend processing, they connect on every invocation to our database. And since our databases are in the same region of AWS on the RDS platform, and they're not huge databases, especially for our developer environments. They're the cheapest, smallest ones, T2.micros. It's not like they have crazy network capabilities or CPU bandwidth. But it tends to be about 10 milliseconds is the latency cost for connecting to the database on every invocation. And so, yeah, that's a cost that maybe for certain types of applications is too high, but for the vast majority of applications, 10 milliseconds in the middle of a function invocation that might be 80 milliseconds long is a reasonable amount of overhead. So it's really about understanding your needs for your use cases and determining what is the best approach. So that's how you can start to integrate some existing technologies that aren't horizontally scalable in the same way that serverless is. I want to venture into kind of a second area of architectural challenges that have plagued serverless as a new tech for a while, and that's rate limiting. One of the really amazing things about serverless platforms is how easy it is to spin up hundreds and thousands of functions that are all doing something interesting. Something that people have effectively used serverless for has been load testing of APIs, because it is so trivially easy to just spin up hordes of Lambda functions that can then just make HTTP requests against other services. But with that power comes a lot of responsibility. So we had a customer that they had this interesting challenge. They said, we need to be able to scrape websites of our of our partners. This was going to help us do some, business analytics, and we need to kind of keep track of where some of our content is propagating. But we don't want to take down any of our partners. We just want to use their public interfaces to understand a bit more about how our content is being displayed there. So they want to be friendly, but they still need to do a batched task that is very simple to do in a Lambda function, but they don't want to spawn millions of them all at once. So that's our scenario today. And we're going to kind of walk through how to build a system where you're doing rate limiting with serverless tech. Breaking it down a little bit again, a rate is simply a quantity, a measure of something over time. So if we start with that and we start to think about, well, how can we how can we operate on a quantity and how can we operate on a period of time? We can start to build up a system. So as an example, we might say that we want to limit to 60,000 network requests per hour. So we dial it back a little bit and we refine it. We say, okay, that's 1,000 requests per minute. So if we start to think at a high level of how we might implement this, we can kind of flip it and say every minute, let's scrape 1,000 pages. So how do we do that? On the time component, we need a heartbeat generator, something that is going to cause a series of actions at a steady interval of time. So all of the cloud providers have some mechanism for doing this. AWS CloudWatch events, Azure has timer triggers. GCP way back, a year ago when I first started building this, it's a little bit more challenging. App Engine, cron jobs plus App Engine plus pub sub to invoke your functions. I think it's actually quite a bit easier today. They all have this mechanism for executing something on an interval of time. So we have a way to say invoke a set of functions every minute. But how are we going to make sure that we make 1,000 web requests every minute? We're going to need some amount of concurrency because a given Lambda function is not going to be able to create 1,000 network requests in a minute. So we measure a little bit, and we realize that we can safely do 20 requests per minute per invocation of a function. So what that means, a little more math, simple, we need to be able to run 50 concurrent functions. So how do we make sure that we're only running 50 concurrent functions and not 200, let's say? Well, we can do a couple of things. The first solution is, let's trigger the functions manually. Every minute, we grab 1,000 pages to scrape from a database, a DynamoDB table maybe, the list of pages here. And we've got this invoker function, and it's going to invoke 50 of these scraper functions every minute. And it's going to give them 20 pages each. And this is nice because it's very configurable. I can just use some constants to determine the batch size and how concurrent it is. And it's also very cheap. It's pay-per-use cost. It's perfectly in line with all the benefits of serverless. But there's some cons to this approach. There's not any great retry capabilities built into the system. So we can look at other options. A fillable queue. It's not really a technical term, but it's a concept of, I might have a queue somewhere where I'm just going to keep adding messages at a steady rate to it. And as I add messages, that will inherently invoke functions that are waiting for messages from the queue. And most of these queues have aspects of being retryable. So if you've got a queue and you've got a function listening to that queue, if that function dies in the middle of processing an event from a message from that queue, the queue's going to hold on to that and re-invoke that function. So there's a couple different providers of these queues. There's native queuing services, which we'll look at. And there's also some NoSQL databases that you can use. So let's look into what those look like. Our second solution, we'll use like a partitioned queue, like AWS Kinesis Streams or Azure Event Hubs. These are similar to Kafka as a message queuing system. So you've got the ability to provision a queue and control the concurrency by how many partitions there are in the queue, because every partition is going to invoke one function with a batch of messages. So we talked about how we needed 50 functions to be running at once. So we need 50 partitions for our concurrency. So every minute we have got a function that's going to add 1,000 pages to this queue. And that's going to cause 50 scraper functions to be invoked with a batch on average of about 20 pages each. So on the plus side, we're adding in our ability to retry things. And it's very configurable again. We just set how many partitions of our queue that we want. And that sets both our batching and our concurrency. But on the con side, it's extremely expensive because AWS Kinesis Streams, Azure Event Hubs, you pay per partition. And at least in the case of Kinesis Streams, every partition is about $11 a month. So you're paying now $5,500 a month just in streams. So it's probably not a solution that's going to work well. So let's look at another option. Really interesting components of DynamoDB and many of the other NoSQL hosted services is that they're key value stores that provide a stream of change events when you operate on that data store. So every time that you add a record, delete a record, change it somehow, it causes an event message to be generated on a stream that is intrinsic to that database table. So we can use this. We can say, again, we've got a fill queue function that is going to, every minute, add 1,000 pages to the key value store. Each page record then is batched into a certain number of, a certain batch size, 20 messages, that are going to invoke our scraper function. But while concurrency here is very possible, we don't get to configure it. The stream that you get dynamically scales up and down according to heuristics set by the service provider, not by configuration that you provide. So we may not get 50 different partitions in our stream. So we're not sure that we're actually going to get our full concurrency that we need. So while it's a proper stream, it's retriable, and it's somewhat configurable in that we can set the batch size. And another positive aspect is that you've got some queue visibility because you can actually query the table to see what is in there waiting to be processed. On the downside, you can't configure your concurrency, so you can't actually be sure that you're meeting the rate that you need to be hitting. And it's still slightly expensive. You have to pay for your key value store throughput. Make sure that it matches the load that you have. So it's still not the greatest solution, but it was the best. One of these three solutions was the best solution we had for like the first 4 years of serverless computing. Thankfully, in the past year, like about 6-9 months ago, we finally got a solution that works really well. And that's to use a proper job queue like AWS SQS. So the way that this works is it's a horizontally scalable resource, a message queuing service, but you pay per utilization of the number of messages that you invoke and dequeue, rather than having to pay for a certain throughput, as you did with a Kinesis stream. So this becomes somewhat more trivial now. We've got the ability to add, every minute, 1,000 messages to the queue. And each of those page records is batched into 20-page messages that are going to invoke our scraper function. And this just happens automatically. Concurrency, the queue is just going to create those batches, and it's just going to fire off as many functions at a time as it needs to. On top of that, if you want to be really secure, you can use something called reserved concurrency that ensures that only an X number of functions is going to be invoked. So on the plus side, we finally have a cheat model that works. We've got the ability to have retries that are built into the model. And concurrency, as I mentioned, it can be safety limited using this reserved concurrency concept. On the downside, and the only real downside, is that the concurrency safety limit, in the case of AWS Lambda, you start out with 1,000 functions that you can run at one time. If we go and reserve 50 for this rate limiting example, that means that we only can have 950 other invocations of other functions, no matter what. So setting that concurrency safety limit decreases the available concurrency limit for other functions. So to counteract that, you need to make sure that you're always increasing your total limits for concurrent Lambda invocations. But that's something that you can manage. So in the past, there was this list of things that you had to choose, you had to think about to choose between the first three options. Thankfully, that's not a thing anymore. And we've got this ability to simply use SQS job queues. You just have to remember to increase your concurrency limits. Lastly, I want to talk about state management. So this is an interesting concept. There's some solutions available out there. It's all about, I've got like a flow chart of steps that I need to execute. And you can imagine that every colored circle here is a function that's going to execute some business logic. That's then going to move the state of this state machine into the next rectangular box. And so you want to build this system up. But when all you have is Lambda functions and DynamoDB tables and streams and topics, it can be hard to figure out, well, how do I actually implement this, especially if I want to do it in an arbitrary generic way. Well, if we break down what you need to build a state machine, you need two foundational things. You need the ability to coordinate concurrency so that if you need to do like a map reduce, where you're going to spawn off 100 functions, and then when they're all done, you're reducing the results into the next state. We need some way to manage all those 100 functions. And we need an ability to manage state transitions. So how do I get from one state to the next state when I'm just one function in the middle of a large state machine map? But if we have solutions to these two core challenges, it turns out that we can build any serverless state machine with those solutions. So let's look at how we can implement solutions for these challenges. Concurrency coordination inherently requires external state. So let's look at an example. Part of Stackery as a product, it builds entire application stacks for our customers. And part of that process is going through and looking at all the applications that are in their serverless stacks and building them in parallel. So if you've got Node.js functions, we're running npm install. If you've got .NET functions, we're running .NET build. And we want to build all these functions in parallel. So it's effectively a map reduce style state machine. So that's what we see diagrammed up at the top. Got a splitter function that's going to invoke, say there's 5 functions in an application. It's going to invoke 5 instances of the builder function to build those. And then at the next, once those 5 functions have been built, we need to go to the next stage where we're going to create what's called a CloudFormation change set. But how do we know when we're in the builder function that we're, say, the last builder function to complete? So what we can do here is our splitter function can add a record to a DynamoDB table, a database, with a count of the number of concurrent invocations that we're going to invoke of the builder. So we're going to say we've got 5 builder invocations. We're going to perform those invocations, and at the end, we're going to atomically reduce that count in the database. So going 5, 4, 3, 2, 1. Finally, the last builder completes, and it gets down to 0. Once we get to 0, we, as the builder function, know we can transition to the next state. So this table up at the top right, that's a list of our functions. That's the external state, external to the builder function itself, that we need to be able to coordinate concurrency. So then that's one solution for the first challenge. The second challenge is, how do we implement state transitions? How do we, as one function, know where we're going to go for the next state in our state machine? And contrary to concurrency coordination, where we needed external state, for this we actually need some kind of local state. Let's look at another example. We've got a different state transitions diagram here, application diagram. We've added a loop where, say, the builder function fails. Maybe it's a temporary failure because we're building a node function and NPM has a hiccup, and so we couldn't build that function the first time. So we're going to attempt to execute our builder function. And we need to know what to do. That on failure, we want to go back and retry, but only a certain number of times. We don't want to have an infinite loop. So every time that you invoke a function, you're passing a message to it. So when you're starting out, maybe we've got a retries property of that message that's set to 0. But when the function fails, we're going to check that retries message. If it's greater than a certain number of maximum retries, then we're just going to report the failure. We're going to invoke a failure handling function. Otherwise, we're going to increment a retries count in that message that we received, and we're going to re-invoke ourselves. So we're using the message itself as we re-invoke ourselves as that local state that helps us understand where we need to go. So all of this, state management of where do we go next is codified both in the source code and in the message that we're passing around as part of our state machine. So is there a way that we can make these two concepts more general, to have a framework, so we're not working at a very low level? And it turns out that there's two services today that make this fairly simple: AWS Step Functions and Azure Logic Apps. The challenge is that they're very expensive. They were built under certain assumptions that they would be used for regulatory compliance, where you need to make sure that everything is executed exactly as many times as is logged and as is expected, that there are logs that can be audited with legal regulation compliance. So they tend to be very expensive and inappropriate for high throughput applications. Instead, a really interesting technique that Azure has put out is a library called durable functions. And that's where they actually tie together for you the external state using Azure tables and internal state via the library and the messages that it generates between the functions. And it kind of handles all of this on your behalf. And because it's a client library and not a service, you have the ability to decide what levels of logging and sort of scalability concerns you want to deal with to control cost. So it's very flexible. So we've talked today about 3 examples of how to build serverless solutions for typically non-serverless problems. My goal is that with this you'll see that there's a lot of great use cases where serverless just fits hand in glove. But even when it doesn't, there tends to be other solutions that you just need a little bit of engineering to kind of find the right techniques. And with that, you can still bring down your total cost of ownership. You can make it easier for everyone on your team to have their own environments. Because this is a serverless paradigm, there are mechanisms for building complex applications using serverless technologies. So hopefully you feel capable of going forth and doing more with serverless than maybe you have before. And again, all this comes from what we've learned as we've kind of observed and built our own high-performance serverless team at Stackery. We've delved into what really makes it possible for people to ship releases of software and fixes faster. And it really boils down to three main things. How do you manage configuration? How do you collaborate? And how do you provide a layer of consistency around it all? So as a small plug, you can figure all that stuff out on your own. You can find someone who you can consult with to help you figure it out, or you can go out and find a tool that helps accelerate your team. That's what Stackery does. We help in many different ways, but the easiest thing that gets people excited, it's partly just that it even visualizes your application architecture, taking your AWS SAM or serverless framework application, importing it, showing it to you, letting you edit it, add new resources, wire them up to create permissions and be able to reference resources across each other, helping with deployments, all the things that teams need to be able to be high performing, you get out of the box with Stackery. So with that, I want to thank you for allowing me to come here and talk, and I'd love to answer a few questions as we have time. Thanks.